Imagine standing on a pitch-black highway
Mm.
at midnight. You're staring directly into the blinding headlights of an oncoming semi-truck, and you're trying to spot a matte black sports car speeding right next to it, but, with its lights completely off.
Which is pretty much an impossible task.
Right. But that is exactly what Earth's planetary defense system is trying to do right now. So welcome to today's deep dive. Our mission today is unpacking a completely revolutionary concept called the Geodesic Shield.
It really is a massive paradigm shift.
Yeah, it's a framework that transforms planetary defense from simply looking through telescopes into actively enforcing a secure planetary border.
Okay, let's unpack this. Why are those giant telescopes we've relied on for decades suddenly falling short?
Well, it comes down to a fundamental physical limitation. They rely almost entirely on reflected light, and that creates two massive blind spots. First, there's the sunward blind spot, which is exactly your highway analogy.
Oh, because the sun is the semi-truck headlights. Exactly. Asteroids approaching from the direction of the sun are completely hidden by the solar glare. And second, we have what researchers call a decameter detection deficit.
Wait, what does that mean?
Basically, we're fantastic at spotting the massive city-killing space rocks because they reflect a lot of light. But we are essentially blind to decameter-scale objects, so things between roughly 1 and 50 meters across. They're too small and dark to bounce enough light back to our lenses.
It's so easy to think a tiny rock isn't a big deal, but we've seen what happens. Remember the 20-meter asteroid that exploded over Chelyabinsk back in 2013?
Yeah, that was a huge wake-up call.
It really was. It blew out windows, injured over 1,000 people,
Yeah.
And literally nobody saw it coming until it actually hit the atmosphere. Plus, why you should care is that a completely unseen rock as small as 1 meter could instantly wipe out the exact satellite powering the GPS or, the cell service on your phone right now.
Exactly. And because we rely on light, our hazard scales for assessing these threats are incredibly volatile. Take asteroid 2024 YR4. In late 2024, probabilistic tracking triggered a terrifying level 3 on the Torino scale.
That gave it like a 3.2% chance of impact, right?
Right. So we waited, we guessed, and we basically panicked while waiting for more data.
And then suddenly that probability just dropped to absolute zero.
Yeah, it's called a Torino jump. We only had partial light data, so the mathematical models just swung wildly until we got another visual glimpse.
Okay, here's where it gets really interesting.
Mm-hmm.
Because optical light-based tracking is fundamentally flawed, the paper proposes we shift to a completely different physical paradigm. We track geometry.
Yes, specifically relying on Riemannian geometry.
But hold on, you're losing me with Riemannian geometry.
Mm-hmm.
If we aren't using light, how are we actually seeing anything in the exosphere? Like, what is detecting a dark rock in the vacuum of space?
What's fascinating here is the actual mechanism at play. It's called curvature vision processing, or CVP. Instead of waiting for a pixel of light, CVP sensors measure the physical wake the object leaves behind.
Oh, wow.
Yeah, it looks at thermal curvature. Essentially how the intense heat and mass of a speeding asteroid slightly warp the local space around it.
Wait, so we aren't actually seeing the rock at all. We're just measuring the geometric dent it makes in the exosphere and the atmospheric pressure waves.
Precisely. As that rock hits the exosphere, it creates actual hypersonic shock waves. The system detects those manifold deviations deterministically. It instantly characterizes the threat, which completely bypasses the massive data bottleneck of those huge observatories.
Which makes perfect sense. Because the system can track physical disruptions deterministically, it totally shifts Earth's defense from passive scientific observation to active border control.
It does. It utilizes what's called a four-lattice architecture. Under this system, which is governed by the Dillon framework, literally everything crossing that boundary needs curvature credentials.
So it's basically automated passport control for the exosphere. Like, if you don't have an authorized zero-emission map credential, you just get flagged immediately.
If we connect this to the bigger picture, it changes everything. Uncredentialed entries, like meteors or debris, trigger a 30 to 300 second early warning using 4D predictive geometry.
That's a huge leap forward.
It really is. And a highly stable omega calculus completely replaces that volatile Torino scale. It's replacing a wait-and-see model with a deterministic govern and predict framework.
So what does this all mean? It means planetary defense is evolving from passive stargazing into an active, automated shield. But I want to leave you with a final thought to ponder today.
It's the big one.
It is. If the Geodesic Shield treats Earth's exosphere as a sovereign boundary requiring credentials for entry, what happens when human-made hypersonic debris or uncooperative satellites are automatically flagged and targeted alongside natural asteroids? Who actually gets to govern Earth's unified border?